Recording on this computer. Now we're going. Good stuff. So this is our second week of ANSI testing, and I have uploaded a few new slides as promised last week, because where we will begin today in our lovely little set of notes will be right here on page 2 of our ANSI test notes. So scroll on down, moving on down to where we get to our weird little gain terms. Now, right from the top of page 2, put a star at the top there. Gain in dB versus output in dB SPL. All important to remember. From acoustics, always remember gain is stipulated in simple dB because it's a relative value, whereas output is always listed, and same with input, but we'll talk about that in a bit. Output is always in dB SPL. Again, like time, 4 p.m., 6 p.m., Pacific Standard Time, Central Standard Time, those are absolute time values, just to give you an analogy, whereas the term 2 hours is a relative time value. I can add 2 hours to 4 p.m. I can add 2 hours to 6 p.m. But you can't add 4 and 6 p.m. together like that, can you? Okay, it doesn't work. So the term to remember, and you can scroll down right over to here, right there. You can, C-A-N, bold-faced, underline, italics, highlight. You can add an absolute dB value together and a relative value like 1 plus 2 is 3. And here's the most important formula for the rest of your lives as an HIS. Input plus gain is output. And people forget that at their peril. Okay, this one's going to bite you in the rear end again and again, and when students run into difficulty, I often have them home back in on input plus gain is output. It is all about that. Input is the sound coming into your hearing aid microphone. Gain is what your hearing aid is giving to that, and output is the sum total. And thank goodness in our field, you can add them up like 50 dB SPL input plus 50 dB of gain is 100 dB SPL output. Slane and Pimple, like 1 plus 2 is 3. Good. All right. Because you're going to see on hearing aid specs and on ANSI measurements, gain is always read in simple dB. Output graphs are always read in dB SPL. And let's look, just for the sake of historical terms and to indicate where we're going in this field, okay, we're regarding real ear measurement. Look at the term functional gain. Now, functional gain, I'm going to go to a picture of it in our notes, in our PowerPoints here, okay? Now, first of all, to get that, I'll highlight this slide here. You've seen this one, okay? This is ANSI specs. We've talked about this slide. You've got it. We've got all these concepts too as well. You can't add two absolute values together. One machine making 80 and another one making 80 totals 83 dB SPL. I guess that must be a gain of 3 dB because 80 plus 3 is 83. Put that together. Anyhow, here's the situation in our field. Normal dynamic ranges are fairly large, from 0 to about 120, 110. On the right, you will see the reduced dynamic range offered by sensory neural loss. So notice here, the X is at 50. Uncomfortable loudness is the same as the screen to your, as the audiogram to your left. Okay, it's the dynamic range is now shrunk. The floor has met the ceiling. And MCL, most comfortable loudness, is somewhere in the middle, just like it is on the left. And can you see how the O's, the right ear, versus the X's, there's like a 50 decibel difference. But look at the MCL and MCL on the right. There's not a 50 decibel difference, is there? And notice the uncomfortable to uncomfortable, there's no difference. So let's flip this right, let's just look at it this way. If you have A person with a 50 decibel hearing loss, look at the blue X's, and you have 5 decibel input sounds. How much are you going to want to amplify those 5 dB input sounds? Well, you're going to want to amplify them by the full degree of the loss so that those 5 dB sounds are now audible. But if, look at the yellow, let's say your input was average speech. So now you have 60 dB coming into the hearing aid. You don't want to amplify that 60 by the full degree of the loss anymore. You're going to amplify it by less. And if you have a loud sound, where I'm drawing right here, you're not going to want to amplify that by much at all. So you can see that your required gain is going to go down and down and down. Soft inputs, you'd want to amplify by the full degree of the loss, average by about half the degree of the loss, and loud inputs by little or nothing at all. So look at the gold or yellow very carefully, because this was the founding principle of fitting methods. Half gain rule. Look, here's an audiogram sloping down, okay? The guy can't hear the dotted 5 dB line. So what we need to do is amplify it so it's audible to him, okay? Flip it right side up, and you can see the same story, okay? Here's his floor. All I did on the right was flip things right side up. 5 dB sounds on the bottom. You'd have to lift them up by the full degree of his loss to make those sounds audible. But if the input was speech, you can't do that, because speech is 50 to 60 dB HL and 60 to 70 dB SPL, and you cannot amplify input speech by the full degree of the loss. So that was the origin of what was called the half gain rule. And this is functional gain. It's not so long ago. I never got into audiology until my late 30s, okay? And this is the way we measured hearing aids. I'm serious as a heart attack. Real ear didn't exist. You did the unaided thresholds under headphones, as you see here on the audiogram. Then you took off the headphones. Then you put in a hearing aid, and yes, a hearing aid, because people didn't fit binaurally in the late 1980s. They didn't do it, okay? Are you right-handed or are you left-handed? That's the age you're going to get. And they would put the hearing aid in the guy's ear, turn it to a comfortable volume, and set the person 1 meter away from a speaker. This was done all over North America, okay? All over. They called it functional gain. And what you did was retested the guy's thresholds in a sound field. So to stop sharing here, first you tested the guy under headphones, you got the hearing loss. Take off the headphones, put a hearing aid in, turn it up to a comfortable volume, set the person 1 yard away from a speaker, and play warble tones. That's what it would sound like. 125 would sound like an organ. And they used warble tones to reduce any chance of reverberation of the sound from the walls of the sound chamber. That's why they used warble tones, okay? So what you were trying to do was to see what the aided thresholds were. So the little letter A's were the aided thresholds. And see that I'm not improving the hearing up to 0. I don't want to do that. The thought was this: if I improve the guy's hearing by half, that means that input speech, when it comes in, okay, input speech, my output is going to look like this. Okay, it's going to sit somewhere between the guy's thresholds and his loudness discomfort levels. In other words, my aided speech output will sit nicely in the guy's dynamic range. And that is why, WHY, that is how come you amplified by half the degree of the loss. So if you had aided thresholds that were improved by half the degree of the loss, then you supposedly had hit your target. That was your target. That's what you wanted. I wanted my aided thresholds improved by half. Okay, now I know that when input speech comes into the hearing aid, it's going to amplify the input speech so that the aided speech is sitting nicely in the guy's dynamic range. Because if I amplify input speech by the full degree of the hearing loss, the output will be way down here at the bottom, and it'll be too loud. And that was Sam Liebarger's half gain rule. And that's the mother, that is the spinal cord, that is the river that runs under all fitting methods today. Half gain for average speech inputs, more than half gain for soft inputs, less than half gain for loud inputs. How come? It's all because of the reduced dynamic range of the listener. Then came real ear. And real ear came around 1990, 89, 1990, real ear came into the picture. And they called it insertion gain. Now the difference was functional gain is behavioral. The guy's raising his hand. Raise your hand when you hear the tone under headphones. Now raise your hand when you hear the tone with the hearing aid in a sound field. Okay, so what's functional gain when I ask on a quiz? It's the difference between aided and unaided hearing thresholds. Functional gain. Okay, it's behavioral. The guy's raising his hand, aided versus unaided. And you're comparing the difference, and what you want to see is an improvement of half. Okay, in comes real ear. Step number 2. And here you're looking at insertion gain. Now what they did here was they measured the guy's unaided open ear canal resonance. The resonance of the outer ear. They put a tube in the guy's ear canal, and you snake that tube all the way up to his eardrum. Don't touch the drum, bump, it'll feel it. And you have the open unaided ear, and the guy is sitting 18 inches away from the screen monitor of a computer. Now what comes out of the speakers is a sweep tone. Don't think about a broom, because I sweep with a broom, but they call it sweep tone. It means it's going from low to high. And I'm measuring the unaided open ear canal resonance of the outer ear, just what you learned about in anatomy class. And what is that? Well, no given resonance below 1,000 hertz, around 1,500 hertz, I'm starting to get a lift. The peak resonance at 2,700 hertz, going out to about 4,000, and then down again. That little 20 dB lift for the high frequency consonants known as the outer ear canal resonance. Okay, so if we look at our real ear slide, here's R-E-U-R, real ear unaided response. There's the peak at 2,700 hertz. It goes out to about 4,000 hertz and then drops. And it starts picking up beyond 1,000 hertz here. So, and what's the added lift? Around 20 decibels. You can see it. If the input sound was 55, because that's what they do, make it like regular speech, but the tone is going, and it does that a few times, and looky, now you're getting the unaided ear canal resonance. Then they would hold that tube firmly in place and put the hearing aid gently on top of the tube, turn the hearing aid up to a comfortable volume, and have the same sweep tones come in at 55 dB, same intensity, okay? And look at this, real ear aided response. Okay, real ear aided response minus real ear unaided response gave us real ear insertion gain, R-E-I-G. And did that match the target of your fitting formula? Was your fitting formula half gain? Was it DSL? Was it now? Whatever. What was the target of your particular fitting method in question? And did your real ear insertion gain match the target? Okay, that's insertion gain. And then the last one, the way we do real ear today is not this way. There was a professor, and he's just retired. He's an American from Connecticut, but he's done all of his academic life was at the University of Western Ontario, London, Ontario, Canada. Sorry, guys. And his last name is Seewald, S-E-E-W-A-L-D, Seewald, Richard Seewald, PhD. He hated insertion gain, and he hated it and still hates it because he says, well, if you plug up an ear with a headphone during a hearing test, if you plug up an ear with a headphone, you've driven a truck over your real ear open unaided ear canal resonance. You've closed it. You put a headphone on it. So your ear canal is no longer a quarter wave resonator. It's no longer going to have REUR. You just plugged up the ear with either an insert or a circumoral headphone. So for heaven's sakes, if you didn't use REUR during your hearing test, then why the Sam Hill are you using REUR when you're doing real ear? Okay? Let your yays be yay and your nays be nay. If you're lukewarm, he'll spew thee out of his mouth. So basically, forget it. The only reason you should use REUR is if you did your hearing test in a sound field where you had open ear canals. And then you would be using your REURs. But that's the only, and nobody does that. We do hearing tests under headphones. So he had problems. He had what they call issues with it. So what happened was we left it behind, and now we do speech mapping. And this is called an SPLogram from Richard Seewald, and everyone's doing it now. Hey, everyone's doing it, man. So look what's happened. Everything is in DBSPL. Normal hearing in DBSPL. There's minimal audible pressure, MAP, on the bottom. That's 0 dBHL. Is, capital I, capital S, underline, bold-faced, italics, MAP is 0 dBHL on the audiogram. So now everything is changed to SPL. And everything's going up instead of down. So no normal hearing's on the bottom. Here's the guy's hearing loss plotted upward. Look at the asterisks. That's his uncomfortable loudness levels. And what you want to do is say, hey, soft input speech, let's aid it so it's barely audible. It's barely above his thresholds. Because normal hearing people barely hear soft speech, so why should the hearing aid wearer? And then let's take average input speech, the yellow, and let's lift it up where it belongs. Okay, so it's all audible. And then let's make sure loud input speech does not exceed loudness tolerance levels. You have literally mapped input speech for 3 different intensities. So this is what's called speech mapping. And it started with the DSL fitting method. And DSL said, screw it, forget REUR. It's a stupid thing to do in real ear. Forget insertion gain. It's all about output, because output is the groceries that are delivered to your eardrum, to the doorstep of your eardrum. It's all about output. Gain is a means to an end. It's like output is the bread you got from the store. Gain is like me saying, did you ride your bike to the store? Did you drive your car to the store? Did you walk to the store? Who cares? Did you get the bread? Okay, so output has become king. Gain is yesterday's news. Gain is a goner. So now we talk about in situ output. In situ means in situation, hearing aid in place, output. And that is REAR. That's real ear aided response. And they're doing 3 REARs. One for soft inputs, the green, one for average inputs, the yellow, and one for loud inputs, the red. And that's the general story about real ear that we will be following later on in the semester. But right here now, I'm just giving you the instance of where we see it in terms of ANSI, okay? So gain terms, functional gain, the old way, insertion gain, the newer way. Hey, the fitting methods didn't change. Please remember that. When asked on a quiz, fitting methods totally changed with the advent of real ear. True or false? False. What changed was the method of verification. In the early days, they used functional gain to verify or prove whether you were hitting target. Later on, they used real ear, which used insertion gain. So the numbers didn't change, the targets didn't change. What changed was the method in which you verified the targets. One was behavioral, functional gain, and the other one was non-behavioral, insertion gain. And insertion gain had another huge advantage. It was quicker. Candy is dandy, but liquor's quicker. It's faster. Real ear takes about 10 seconds, okay? When you're doing functional gain, you're doing another whole hearing test, aided, so it took way longer. Now, here's Seewald. In situ output has appeared as real ear measurement has evolved into today, okay? REAR is the main focus. REUR only helps to determine accurately whether the probe tube is placed in the ear canal correctly. We'll talk way more about this later, okay? But I'm just giving you a heads up. This is where we're going. We're going to be talking after the midterm especially about the evolution from old real ear to today's real ear, okay? All right. Enough on that. That's just a precursor. I love repeating things. I like to throw things out, and then later on we'll mention them again, and it'll be like watching the movie the second time. Oh yeah, that's right. I heard of that's the way I like to go. 2 steps forward, 1 step back. So let's look at our ANSI procedures on a hearing aid test box. This is sort of like I'll have a sip of coffee here to mark that this is a change now in topic. Gargle. Good thing I didn't spit it out. Okay, here we go. The first ANSI measure is called OSPL90. Old days it was called saturation sound pressure level with 90 coming in. Now when you think about SSPL or OSPL90, what I want you to think about is this slide here. The hearing aid is bloated. Now this is going to be slide 44 out of 60 in your PowerPoints. Look at the shape of that output. Look at how it's kind of almost like my cheeks. The sponge can only hold so much water, okay? If you lay a sponge in water, it can only pick up so much water. Same with the hearing aid. It's like, what is the hearing aid doing with the pedal to the metal? Floored, gas pedal to the floor, downhill with the wind. Okay, what is the maximum output that the hearing aid can possibly produce? With 90 coming in, volume full blast, what's the maximum out that a hearing aid can do? And you'll see an example. This is just some maximum power output, or OSPL90, same thing, of a BTE measured in a 2cc coupler. All right, you and I both know that in the real ear canal, we need to look at RECD. You'd have to add about 5 dB below 1,000 hertz, 10 dB above, and you'd get an idea of what that'll do in the real human ear, but nonetheless, this is ANSI. So what's my peak output here? 130. And BTEs, the number 13 tubing BTEs, they often still do have a main peak at 1,000. That's how you can tell it was a BTE, just by looking at it. Now, I don't mean RICs, and I don't mean thin tubes, but number 13 high power BTE hearing aids. Okay, now look at this here carefully, because the second thing that OSPL90 looks at is not just the curve and not just the peak, but also the HFA. high frequency average. So you're looking at the output at 1,000 hertz. Mark it down. Here it would be 130, something like that. What's the output at 1,600? Follow my cursor, 1,600. And you scroll up, 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 and you'd see it was about, probably about 125. And then what's the output at 2,500 hertz? High frequency averages 1,000, 1,600, 2,500. Those three frequencies are added up and divided by 3 to give you your high frequency average, OSPL 90. So 1,000, maybe it's like 129, 1,600, it's probably about 125, 2,500, I don't know, something like, 122, whatever the heck it is, add them up, divide by 3, that's HFA OSPL 90. And when you look in your notes, what does it say? Purpose is to find the maximum output the hearing aid can possibly produce. This is where the hearing aid is saturating and can't put out any more SPL. Procedure, volume control, full on, input 90, and here a frequency sweep is run. Hearing aid test box calculates the output, and it shows 3 things. Here you go, the response curve, the high frequency peak, and the high frequency HFA average. And that should be within plus or minus 4 dB of the hearing aid specs. And I wrote in italics here, note saturation responses like OSPL 90, they always look flatter than gain responses. That's because the hearing aid is bloated, okay, literally. All right, back over to here. Go one slide earlier. There's the same hearing aid. This is called full-on gain, FOG, F-O-G, full-on gain. The volume is still full blast, but now only 50 or 60 is put into the hearing aid, less than 90, 50 or 60. And the second thing is, not only has the input gone down, but you're no longer looking at output. Now you're looking at dB gain. Okay, so 2 things happened when you moved from OSPL 90 to the second ANSI measure, full-on gain. One is the input was reduced, and secondly, you're not looking at output, you're looking at gain. And look at the frequency response here. Can you see how there's less in the lows and more in the mids and highs? And doesn't that make sense? That's what most people have, as a high frequency loss with better hearing in the lows. Presbycusis goes down. And so my full-on gain is going to have a different shape than this. See that, how it's bloated? And here it's not. All right? So think of one's cheeks being, okay, and here you're not. You're looking at the gain. So 2 things have changed. Let's look at our notes. Full-on gain. Purpose is to find the maximum available gain in the hearing aid. The input does no longer causes saturation, okay? Because your input went down. Your volume is still full on. Your settings are still full on. And the same frequency sweep. And the hearing aid does not. Some here, now this on some ANSI test equipment you will see a response curve, and on some ANSI test equipment you won't. So it depends on the equipment you're using, okay? But the point to notice here is 2 things have changed. One is you're no longer looking at output, and the second thing is you're looking at less input coming in. And let's just, for the sake of good old exercise here, what's the gain at 1,000 hertz? If I showed on a quiz or a midterm this particular picture, and I asked on question number 1, what's the gain here? And you'd have to look at this and go, at 1,000 hertz? Yeah, okay. That's about, let's just round it off, 130. So what's my gain? Well, what was my input? 90. So 130 minus 90 is 40. That must be my gain. Remember, input plus gain is output. What's my gain over here where my cursor is now? Well, the output's 125. What was my input? 90. 125 minus 90 is 35. I guess that must be my gain. Okay? So now let's look at full-on gain. Look at this. Now my gain is 60, 65. How come that can be? When over here it was, whoa, when over here it was only 40 or 35, and over here it's like 60 or 70, 65. How come? Because my input is less, and because the hearing aid is no longer bloated. Okay, just food for thought. All right, now we run into our third measure in ANSI. So we work our way down to number 3. Reference test gain. Now, the input is left the same. The input is like 50 or 60 to imitate average speech. That's why 50 or 60 is chosen, to imitate speech. But now something else has changed. Now you've gone in and reduced the volume setting of the hearing aid. You've reduced it. Okay, and they tell you there's all kinds of stuff here about 17. I don't expect people to sit and memorize this, so please don't think you have to sit there and memorize what I'm highlighting here. I put that in FNO, for nerds only, or freak not out, okay? But the point of reference test gain is reduce the volume to more of a user setting. So now, not only is the input like regular speech, but also the volume setting is like regular user setting. So can you see the flow so far? Look at the flow, okay, from output. So I'll scroll up to number 1 here. OSPL 90, pedal to the metal, maximum output. Then full on gain. Oh, let's reduce the input to be more like speech. And let's focus on the gain here. Look at what the maximum gain is. And then step number 3. Hold that thought, but now let's reduce the volume. Keep that input like regular speech, like step number 2, but now reduce the volume to more of a user setting. So reference test gain is meant to show what's the hearing aid doing in everyday life. On the client, what's the hearing aid doing? Okay, so the purpose is to show the gain for typical speech input with typical volume control position, real life performance. Gives an idea as to how the hearing aid will function in real, good old, everyday life. And when you scroll down to the bottom here, you'll see it'll show you a frequency response. And it might be in terms of output. Here, just qualify this, okay? On some equipment, it might show it in terms of gain. And on other equipment, it will show it to you in terms of output. Either way, doesn't matter. But let me give you an example. Let's say you are going to a hearing aid. I'll just give you an example here. If I scroll down this away, here you go. Okay, this is going to be OSPL 90, the thick line. And you can see all of it explained here. What's my input? 90, 90, 90. What's my peak, my maximum? What's my HFA? Okay, and then look at this dotted line. Reference test gain. And they're showing it to you all in output, output, output here. So what was my gain? Well, looky, looky, here comes Cookie. What was my input? My input here was 50 or 60. So with the gain of, see, you can see my input here was 60. So what was my output? Well, I guess my output might be around 100. So what's 100 minus 60? 40. Okay, so even though this reference test gain, this dotted line that I'm showing you with my cursor, is plotted in terms of output, I'm going to be asking you, what was the gain here or here or here? And you'll have to say, well, what was the input? Okay, then I can subtract the input from the output, whatever it was, and I'll get my gain. Always remember, input plus gain is output. And then measurements 4 and 5. And that does it. That finishes ANSI. So look at measurement number 4. EIN. So the hearing aid is left at reference test gain position. Your volume is reduced. Your inputs are the same. Okay? And what is EIN? The internal noise generated by the hearing aid. And just to take this home, if I'm sitting here in front of my laptop computer talking on Zoom session, if I'm quiet, I can hear my computer hum. That's internal input noise. Okay? EIN is what's the noise being made by the hearing aid? What's the internal junk? What's the microphone noise, the receiver noise, the amplifier noise? What's the crud produced by the machinery of the hearing aid? And that is measured at reference test gain position. So the volume is reduced. You've left it reduced. So you've gone from OSPL 90 to full-on gain, and then you've reduced your volume control. Now you're at reference test gain, and then at reference test gain, EIN is measured, and total harmonic distortion. First, EIN. It's the internal noise from the hearing aid, and it better be under 30 dB SPL. Okay, because if it's not under 30, it won't pass. And a person with decent low frequency hearing is going to hear the internal noise of the hearing aid. So the EIN has to be under 30 dB. So look at EIN here. Purpose to determine the internal generated noise of the hearing aid. Concerns mainly the mic and the amplifier. Procedure, volume control left at reference test gain position. Input is 60 dB. So you're measuring the output, and don't worry about this blah, 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 about these two sentences right here. You can read them if you want to. FNO for nerds only, or freak not out, but the point is your EIN should be 30 dB or less. Okay, and what's the tolerance? Plus or minus 3 dB. Good. Last one, harmonic distortion. Harmonic distortion is also measured at reference test gain position. Volume control is still there, but now you're looking at something different. With total harmonic distortion, you are measuring what's the hearing aid adding to the signal. You're not looking at the internal noise of the hearing aid. If a little 500 hertz came into the hearing aid, did a big 500 hertz come out? That would be what you'd want, okay? But often in reality, what happens is a little 500 hertz comes in, a big 500 hertz comes out, plus a little 1000 hertz, and a little 1500 hertz, and a little 2000 hertz. In other words, you invited Mary to the party, but unbeknownst to you, Mary brought her 2 kids along. That's not what you had in mind, okay? There's some harmonic distortion happening here. So what happens is THD, total harmonic distortion, is what's the hearing aid adding to the signal coming in? Not the internal noise. That's a different kettle of fish. That's the noise made by the mic and the amp and the receiver. I'm talking about if a hearing aid, and that's why the input sounds are 500, 800, and 1600 hertz. They're all lower frequencies. Why? Because what are the harmonics of those frequencies? So if you have a 500 hertz tone, what's the next harmonic? 1000. And if you have, what's the next harmonic? 1500. And the next one? 2000. Okay, now try 800 hertz. What's the next harmonic? 1600. What's the next one? 2400. What's the next one? 3200. Okay, and then you have the final frequency coming in, 1600. What's the next harmonic? 32. What's the next one? 48 or whatever, you know what I mean? Like and that's why your input can't be 4,000, because what's the next harmonic? 8. Well, now you're out of the range of hearing aids. So when you're looking at total harmonic distortion, you have 3 input frequencies: 500, 800, 1600 hertz. Okay, those are the 3, and you're looking at a tolerance of less than 10%. At each of those frequencies, you want less than 10% harmonic distortion. So a real true-false question I often ask on a midterm is, okay, total harmonic distortion should be less than 10 dB. True or false? And the answer is false. It's less than 10%. What's the only ANSI measure to measure in percent? Harmonic distortion. All the other ones are dB. So those in all essence are the 5 ANSI tests that you should all know. OSPL 90, full-on gain, reference test gain, equivalent input noise, total harmonic distortion. And these last 2 are measured with the volume control at reference test gain position. I'll kind of take it home too, because some weaker hearing aids, mild gain hearing aids, you won't have to reduce the volume control, because if you did so, it would be reduced too far. So in other words, you're going to see on your ANSI testing, when you're moving from full-on gain to reference test gain, the ANSI box will stop you and it'll say, please turn down the volume. It'll be blinking, 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 and you'll have to go manually open up the box and reduce the volume until you, yep, okay, there I am. Close the box, hit go. And it'll do reference test gain, equivalent input noise, total harmonic distortion. But weak hearing aids, when you see that little box going, turn me down, turn me down, turn me down, it'll already be down because the hearing aid is weak. And so there would be no volume control adjustment necessary. Anyway, but that's just a caveat, though that happens once in a while. So here's harmonic distortion. Measure distortion that occurs from the hearing aid. Is the output proportionate to the input? These are frequencies in the output which are multiples of the fundamental frequency. For lows, these distortion products can be seen and thus indicate distortion provided by the hearing aid. Procedure: volume is at reference test gain position, input of 5, 800, and 1600 hertz. Do distortion, do harmonics occur? Low frequencies are used because harmonics are equal multiples of these fundamental frequencies. If highs were used, their harmonics would occur outside the response of the hearing aid receiver. The tolerances should be less than 10% at all test frequencies and should be within plus or minus 3 dB of specs. Okay, now we're almost ready to sign off, except for one thing. Your cochlea is an amplifier. Your outer hair cells amplify. And no amplification takes place without distortion. If we were in heaven, I suppose we could amplify with pure perfection, but we're here on earth. We can't. So all hearing aids will have some harmonic distortion, and all amplifiers will, and so does your cochlea. And what are the harmonic distortions of your cochlea? Otoacoustic emissions. OAEs are harmonics and sounds coming back out of your ear, believe it or not, a backward traveling wave, hitting the footplate of the stapes, which moves along the incus toward the malleus, and now the eardrum is a speaker. Your eardrum's a tiny little speaker, and it's emitting sounds. And those are otoacoustic emissions. And if you don't have those, you don't have outer hair cells. In this case, you want the distortion, because if you can't measure it, your cochlea isn't naturally amplifying soft sounds below 50 dB. Isn't that wild? So babies are tested with OAEs. If you go to St. Louis, or I think even Springfield, if you go to a children's hospital or go up to the Northwest Pacific and walk into Portland, Oregon, and you will see infant hearing screening done. And audiologists are testing infants to find OAEs. If they can't find OAEs, it's hearing aid time. You got to fit the baby with hearing aids. Because if the baby isn't hearing, baby isn't going to talk. Okay, so pediatric audiology is a real whole field. And if you can fit a baby, you can fit an adult. If you can drive a transport, you can drive a Volkswagen. But if you can drive a Volkswagen, doesn't mean you can drive a transport. Fitting an adult is easy peasy Japanesey. Try fitting an infant of 3 weeks old. Okay, you have to do real different techniques to find out what their hearing is. And they use all kinds of non-behavioral tests because a baby isn't going to raise his hand when he hears a tone, okay? So the whole field is different. But it's just, how about all of that in a talk on ANSI? Well, ANSI, one of the measurements is total harmonic distortion. Why? Because hearing aids are amplifiers, and amplifiers distort. And you don't want total harmonic distortion in hearing aids. I mean, that's like, no, I don't want it, but oh well, you got it. Hope it's less than 10%. In people, you want that emission. You want that distortion because it proves that the amplifier, the outer hair cells of the cochlea, are working as they should. Okay, and so if we stop sharing or we share screen, you'll see stuff in the notes that you don't need to know. Okay, I just talked about this now, the cochlea as an amplifier. And I would put a star by that puppy too. But that's as far as we go in ANSI measures. Because if you look at the bottom of your page, ANSI does more testing too, but not everybody does this. Oh, it tests the battery current. Oh, geez, you can test the induction coil sensitivity, the T-coil. You can test the input-output function at 2,000 hertz to talk about its compression. You can talk about the quickness of its compression, the attack release times. You can talk about the directional microphone. I mean, it'll do all kinds of things. But the main 5 are Matthew, Mark, Luke, John, and I think what's the next one? Acts? I don't know. Something like that. Okay, so the first 5 are generally the ones of most importance in ANSI testing. So basically, this completes our ANSI testing coverage in HEAR 250, okay, real ear measurement. Next week, what we should do is make sure that we go through fitting methods. We'll be talking more about functional gain, the half gain method, stuff you covered in 150, but just to have a good review of it so we're all singing off of the same page. Okay, so for the ANSI section, if I look in the notes here and we start off at the very top, I'll just say, okay, that's something to focus on is the fact that the 2cc coupler is larger than the real ear, okay? And because of the fact that it is larger, and what do I mean by the real ear? Larger than a closed ear canal. A closed ear canal has 1 to 1.5 cubic centimeters, not 2, okay? So the reason KEMAR has a more real or accurate type of ear canal resonance or ear canal volume, okay? And KEMAR, you should know what it is. It's a mannequin that all manufacturers use, and it has a smaller than 2cc coupler. And the fact that the outer ear is smaller, or that the closed outer ear canal is smaller than a 2cc coupler, gives rise to real ear to coupler difference. And have a good idea as to real ear coupler difference and basically what it is, how much you have of it. Okay, and maybe I even have the slide up here again, maybe I don't know, but yeah, here's my picture of it. Okay, out of my little textbook, this is the picture I drew. Okay, RECD, about 5 dB below 1,000 hertz, about 10 dB above 1,000 hertz. So if your ANSI spec is giving you, let's say, the dashed line in the human ear, because it's smaller than a 2cc coupler, you'll basically see the solid line. And that's what a lot of these pictures here are showing you as well. in your PowerPoints. The difference between KeyMar, your simulator, and a 2cc coupler. That's what all these pictures are showing you. So when you're looking at that, this is what it's highlighting is RECD. And then, of course, after RECD, we got into our functional gain, insertion gain, in situ output, and stuff and things. All right, I'll stop sharing. Basically, we're done. Any questions that anybody has? Good to go?
Good.
Great. I'm going to have a coffee. And I think I have Anatomy 120 to do in about an hour. This is my real OTC day. I do 110 in the morning, and then I've got this one, 250, and then 120, and then I can take this out. All right. We'll catch you later, Megan.
Bye.
Bye-bye.